Okay, let's get right into it. Welcome to the ultimate GCSE Science Revision Bootcamp Explainer. I am beyond excited to be doing this with you today. Look, whether you're just trying to lock down those foundational marks or you're really pushing for the absolute top grades, we are going to make it happen. So clear your distractions because you've totally got this. We're going to break down the absolute essentials of biology, chemistry, and physics straight from the source material. We're turning all that complex science into super clear memory triggers.
All right, let's take a quick look at our 3-week syllabus. Week 1, it's all about core systems. Week 2, we shift gears into structures and transport. And then finally, week 3 is going to bring it all together with applications and particles. Let's do this.
So, week 1, core systems. We're kicking things off right now with the fundamental biological and chemical systems you absolutely need to nail for the exam. First up, photosynthesis, literally the engine of life. The word equation here is absolutely crucial. Carbon dioxide plus water, using light energy, gives us glucose and oxygen. And this whole magic trick happens right inside the cell's chloroplasts. Now, if you get asked about the required practical, you'll typically be looking at a setup with pondweed in water. You're basically measuring the rate of those tiny oxygen bubbles popping up. Simple rule to remember, more bubbles means a faster rate of photosynthesis. Exam tip. Okay, grab a pen, because here is a massive exam tip when it comes to making salts. You need to know the exact difference between strong and weak acids. Basically, strong acids completely ionize in water, while weak acids, they only partially ionize. Look at the pH scale we've got here. You'll see deep reds for those strong acids and purples on the opposite end for strong alkalis. Oh, and when you're writing out your equations for making salts, never ever forget your state symbols. That's S for solid, L for liquid, G for gas, and AQ for aqueous. Examiners absolutely love checking to see if you remembered those. Right, let's switch gears from chemistry over to physics and take a look at the standard UK plug. It's like a really important color by numbers. The blue wire is neutral, the brown wire is live, and that green and yellow striped one, that's your earth wire. Now that live wire is the dangerous one. It carries the alternating potential difference from the supply, which is your AC current, and that makes it highly dangerous. We've also popped the rectangular fuse symbol on the right side there. That is a crucial safety device that will literally melt down to prevent overheating. All right, time for a quick challenge. 230 volts at 50 hertz. That right there is the UK mains electricity standard. Lock those numbers into your brain right this second. If an exam paper asks you for the frequency or voltage of the UK main supply, boom, you already have it locked and loaded. Okay, let's jump back to chemistry and build on that. So, crude oil. It's actually formed from ancient biomass, and we separate it out using a fractional distillation column. It's basically sorted by boiling points. You've got to know your first 4 alkanes: methane, ethane, propane, and butane. The trick here is remembering that as those carbon chains get longer, they get way more viscous, so thicker, and a lot less flammable. But we actually need shorter, more useful molecules, right? That's where cracking equations come in. We literally break them apart step by step to make shorter alkanes and alkenes. And hey, do you remember the alkene test? You just add bromine water and it goes from orange to colorless. Such an easy mark to pick up.
You know, just like we transport crude oil, the human body has its own incredibly complex transport system. The heart pumps blood through 4 main chambers. You've got the right and left atria sitting at the top, and the right and left ventricles down at the bottom. Understanding exactly how this blood flows is critical, especially for when things go wrong. If when looking at cardiovascular diseases, we might treat them using stents to literally prop coronary arteries open, or maybe statins to bring cholesterol levels down, all alongside healthy lifestyle choices, of course.
Recap? Amazing job on week 1. You've just smashed through massive chunks of core science. Let's keep that exact same momentum rolling as we dive right into week 2, which is all about atomic structures, radiation, and cellular transport. So let's get straight into nuclear physics. First up, alpha particles. These guys are heavy and highly ionizing, but honestly, their penetrating power is so weak that a single piece of your homework paper could completely stop them. Beta particles can push a bit further. They'll get stopped by a sheet of aluminum, but they are less ionizing. And then there's gamma rays. Well, these are actually electromagnetic waves. They are highly penetrating. We're talking needing thick lead or concrete to even slow them down, but surprisingly, they're the least ionizing of the 3. Visualizing these differences like this in a table is for sure the best way to keep them straight in your head. Exam tip. Okay, listen up for this one. For nuclear decay, I want you to visualize just subtracting the mass and atomic numbers. An alpha particle is basically a helium nucleus, right? So that's a mass of 4 and an atomic number of 2.
When you write the equation, you literally just subtract 4 from the top number and 2 from the bottom number of your starting element. Easy. For beta decay, it's a bit different. A neutron turns into a proton, so the atomic number actually increases by 1, but the mass stays exactly the same. Practicing this visual subtraction is exactly how you're going to effortlessly score those 4-mark equation questions. Let's pop over to chemistry structures now. Giant covalent structures, like diamond, they require a massive amount of energy to melt. Why? Because every single carbon atom forms 4 incredibly strong covalent bonds. Now compare that to ionic compounds. They can actually only conduct electricity when they're molten or dissolved in water, because that's the only time their ions are finally free to move around. And you can't forget about metals. Their thermal conductivity is absolutely top tier, and that is all thanks to a sea of delocalized electrons just transferring energy like crazy.
Right, back over to cells. Let's quickly contrast our 3 main methods of transport. Diffusion is basically particles naturally spreading out from an area of high concentration to an area of low concentration. Osmosis, it's the exact same concept, but specifically, and this is key, it's specifically for water molecules moving across a partially permeable membrane. Active transport, though, is the rebel. It actually pushes particles against the concentration gradient, going from low to high, which means it literally requires energy from respiration to make it happen. Exam tip. Time to grab a pen, pause this explainer, and actually test yourself on these formula triangles. For kinetic energy, the formula is 0.5 times mass times velocity squared. For gravitational potential energy, it's mass times gravitational field strength times height. Here's the thing. Examiners love to give you the total energy and then ask you to find the velocity or the height backwards, so mastering how to rearrange these is absolutely key. We've also listed out the core renewable resources here, contrasting them directly against the severe environmental impacts of burning fossil fuels.
Okay, we are officially on the final stretch, week 3. Take a deep breath. We are going to master the applied physics, the diseases, and those tricky particle practicals that examiners absolutely love to test you on. Now take a look at the direct link here between viral pathogens and the specific methods we use to literally break the chain of infection. A pathogen, simply put, is just a microorganism that causes infectious diseases. Beside our little diagram of a virus, you'll see the main barriers we use to fight them. Stuff like basic hygiene, isolation, destroying vectors, and of course, vaccination. These are the real-world direct ways we actually reduce the spread of diseases.
Moving on, let's look at electrical circuits. You really need to remember the distinct rules for current here. In a series circuit, the current is exactly the same everywhere. But in a parallel circuit, the current splits down the different branches. And check out the equation P equals IV. That's power equals current times voltage. You can clearly see how directly proportional graphs map perfectly to these relationships. We've also put up a clear comparison of the wavy, oscillating line of an AC current versus the perfectly flat, constant line of DC.
Taking a quick look back at history, Mendeleev pretty much built the entire foundation for modern chemistry by organizing the elements by their atomic weight. But his real genius? He had the foresight to leave actual gaps for elements that hadn't even been discovered yet. This predictive power eventually helped us figure out reactivity trends. For example, if you look at the group 1 metals on the far left, we now know that reactivity actually increases as you go down the group. Why? Because the outer electron gets further away from the positive nucleus, making it way easier to lose during ionic bonding.
Okay, if you get hit with a 6-mark question on calculating the density of an irregular solid, this is your exact step-by-step water displacement method. First, you use a balance to measure the mass of your irregular solid. Next, you fill a measuring cylinder with water and write down the starting volume. Then, you completely submerge the solid into the water. Measure the new volume, and that displaced water tells you the exact volume of your object. Finally, just calculate density by dividing the mass by that volume. Boom, 6 easy marks in the bag.
Exam tip. Finally, let's talk about handling your data. Precision simply means how close your measured values are to each other. But the crucial exam point here is making sure you check your equipment for 0 errors. A 0 error happens when your measuring equipment gives you a false reading when the true value should literally be 0. Kind of like stepping on a scale and it says you weigh 2 pounds before you even put your full weight on it. In chemistry, maybe a mass balance reads 0.2 grams with nothing on it. You have got to account for this to ensure absolute precision in all your measurements.
Recap. And honestly, just like that, you've reviewed everything from crude oil right through to atomic decay. We've gone over the formulas, the key equations, and the core required practicals. When you finally sit down in that exam hall, just visualize these connections and completely trust your hard work. But also, remember that this science isn't just about passing a test. These are the exact same fundamental principles that govern black holes, cure diseases, and power our entire planet. You now have the code to the universe in your head. So what are you going to build with it? Thanks so much for tuning into this explainer, and happy studying. You've totally got this.